Welcome back. We are talking about this property called total unimodularity of a matrix. We're going to be using some special properties of it, but first I thought I would give a general definition of total unimodularity. It's something that is defined even outside, well outside of integer programming and combinatorial optimization. And basically, the definition is that a matrix is called total unimodular in general with respect to some field if its inverse is also in that field. I'll just write down this specific definition for what we are talking about. So a square matrix with entries, let me give it a name, a square matrix A with entries in -1, 0, 1 is called totally unimodular if its inverse also belongs to the same field. In this case, our field is basically integers mod 2. So if A inverse of ij is also has entries in -1, 0, 1. So I should say an invertible. So this is one definition. Now let me give the other definition that we are going to be using, and then we can think about why these two are, one of them implies the other. So the main definition, and so I'll actually label it as the one that you'll typically see in the context of integer programming, and the one that will be also very useful for us, though actually both will be useful, is a matrix A is total unimodular if every square submatrix, so unlike the definition above, this does not require A to be invertible, it doesn't even require A to be square. And of course, if every square submatrix has determinant either +1, 0, or -1. And note that this immediately implies that A has to have entries in 1, 0, or -1, since any individual entry is a square submatrix of A. So I should just note that this implies that Aij is in -1, 0, +1. And let me just note this explicitly. A need not be square. Okay, so now let's see what we can do, what this does for us. So perhaps the foundational result is that if A is totally unimodular and B is an integral vector, then the polytope defined by A and B has integral extreme points. So the result here is that if A is totally unimodular, and then let's say it's an m by n matrix, and B is an integral vector of the appropriate dimension, then the polytope P, or polyhedron, I'm not making an assumption of boundedness, Ax less than B, which is a subset of Rn, so the x such that this holds, has integral extreme points. So this is the obvious connection for us, because if we are solving an optimization problem and we can show that the constraint matrix has this convenient total unimodularity property, then we can just drop the integrality constraints on x. And we've already seen some examples, or I've asserted some that for certain examples this is true. Shortest path, I asserted that this is straightforward to see in max flow as well. And we essentially showed that this is the case for bipartite matching. But we showed it using combinatorial reasoning. We didn't show it by reasoning about the properties of the constraint matrix A directly. So we're going to show the proof of this, and it basically follows from a formula for inverting a matrix. So recall Kramer's rule that basically says that if you have a square matrix, so if M is a square and invertible matrix, and we know that the equation mx equals b has a solution, namely x equals m inverse b, and m inverse can be computed as follows. So xi is equal to the determinant of m, I'll denote it this way, m minus I. Sometimes it's also denoted mi. Maybe that's even more standard. M minus I is a little bit more suggestive. Mi b divided by the determinant of m, or the determinant of m is the determinant of m, and mi b is the matrix obtained by replacing the ith column of m by b. So you subtract, that's sometimes why I like writing m minus I, but mi is standard. Replacing the ith column of m by the vector b. Now, even just writing this out essentially immediately implies the result for us. But let me also remind you of another version of Kramer's theorem, which basically says that this is another useful fact, that if M again is a square invertible matrix, then the ith entry of Mij is equal to the determinant of Aj, sometimes called a cofactor, divided by the determinant of A, where this is the matrix obtained by, this is the, let's see, M is a square, let's call it n by n, invertible matrix. Aj is the n minus 1 by n minus 1 square matrix obtained by deleting the jth row in the ith column. And so it is a square submatrix. Okay, so we can basically see why this holds, but let's just write out the details here. So again, we have what do we want to show? We want to show that P is equal to AX less than B has integral extreme points. Well, we know what an integral, in order to compute any of the integral extreme points, we need to choose a square submatrix. In other words, we need to choose which are the n tight inequality constraints. So let's, following our usual notation, let's note that an extreme point is defined by the n tight inequalities, let's call these B, as we've done before. So B is a subset of 1 to m, where B has size n. And then, therefore, x is defined by A sub B, this is our usual notation that we used, inverse times B. Where recall, A is assumed to be total unimodular and B is an integral vector. Whoops, I need a subscript B, right? I'm only choosing those sets of inequalities. And then we know from the first way that I wrote the fact, xi is equal to the determinant of AB I B divided by the determinant of A. The determinant of A is clearly, of AB, excuse me. It's either plus or minus 1. So therefore, xi is equal to either plus or minus the determinant of A, B, B. What is this? This is, again, deleting the ith column of the square matrix AB and replacing it with the integral column B. And then all you need to do is expand by minors along that column, and it will be plus or minus 1 times the integral values of B times the determinant of the resulting submatrix of AB. And therefore, by assumption, by total unimodularity, this is going to be integral. And then another way to see this, using this, the other fact is that, more directly, x is equal to AB inverse times B. And we said, A inverse, the ij elements of A inverse are equal to the determinant of this matrix divided by the determinant of A, which is, again, it has to be plus or minus 1. So all entries of A inverse are plus or minus 1 or 0. And again, note that we could have also appealed to the original fact, and this gives us an idea of why those two definitions are equivalent. Let me just flip back here. So our first definition of total unimodularity is that a matrix is totally unimodular if its inverse also has entries in minus 1, 0, and 1. But if its inverse has entries in minus 1, 0, and 1, that's just another way to say that A is that every equation of the form AB times x equals B has an integral solution whenever B is integral. So this is essentially, as close as it gets to just being by the definition. So you can see why this is an extremely useful and appealing definition for the problems that we have. Okay, so let's continue. There's also a connection to the dual polytope, and this is also something that's been very much of interest to us when we were talking about matching, the maximum matching problem and its dual, which was the vertex cover problem. Well, initially we have done all this work to show that the maximum matching problem, that polytope is integral, but we couldn't really say anything about its dual. So here is a result that says that if you have, in the presence of total unimodularity, then in fact you can say something about the primal and the dual. So the theorem says the following: if A is a total unimodular matrix, TUM, of course, M is just matrix, and if B and C are integral vectors, not necessarily in 0, 1, of appropriate dimension. Sometimes I just get lazy and I don't even mention that, but I hope it's clear. Then, if we look at the two optimization problems, which are linear optimization duals of each other, minimize C transpose X subject to AX equals B, X non-negative, and max P transpose B subject to A transpose P less than C, both have integral optimal solutions. So, we know none of this should now be surprising coming from what we just proved, because we get that the basic spirit of this is that we have we're essentially what defines any of these extreme points is the inversion of a square submatrix. But you can see that that's not exactly true for the primal anymore, because in this case, in the standard LP standard form that we've given, the matrix X is also has to be non-negative. So it's not quite there, but it's pretty straightforward to see that this follows in the same spirit as what we did before. But let me make it a little bit more clear, and also just state a lemma which is useful to know. So a lemma says that the following are equivalent. T, F, A, E. The following are equivalent. A is totally unimodular. A transpose is totally unimodular. This is immediate. The determinant of a matrix is equal to the determinant of its transpose. If I append an identity matrix below A, then this is totally unimodular. And I can do additional things. So I and A minus A, this matrix is also totally unimodular. So, this is not, I don't think that these are as immediate as the equivalence of 1 and 2. They take a little bit of thought. So actually we'll use one of them. We'll show 3 on the next slide. But again, just to mention, why do we want things like this? What does this allow us to do? Well, it allows us to immediately give a proof of the previous theorem by appealing to our first theorem. So let's flip back here. So here we showed that this polytope here has integral vertices, but if I know that if A is totally unimodular, if and only if I, A, and minus A, then that allows me to do things like also add inequalities and also add equalities, and basically subsume this kind of result, like what's on this slide, into the first result that we showed, because AX equals B is just inequalities defined with A and minus A, since the vector B and minus B is integral whenever B is integral, and so on. So X greater than or equal to 0 is just an identity times X greater than or equal to 0. So this is why this kind of thing is useful, and I'll just note that now proof of result on the previous slide follows from our first theorem, which was what, on the second slide or something. Let's have a look at this result just to see how it goes. So let's prove a part of it, and the rest of it is quite similar. So let's show A is totally unimodular. Let's show that implies that the matrix A identity is totally unimodular. Clearly, by definition of total unimodularity, the converse holds immediately, because any square submatrix of A is a square submatrix of a bigger matrix that includes A as a submatrix. So that's easy. So what do we need to do? We need to show that, let me write it this way, if this is A and this is I, then any submatrix, any square submatrix, which means I get to select any k rows and any k columns. I'm sorry, I said it in reverse. Any k columns and any k rows, and then the square matrix would be the intersection. So I need to show that this thing has a determinant that is +1, -1, or 0. Clearly, if I choose something that's just a subset of A, then it immediately follows. So, and if I just choose a subset of the identity, then that also clearly follows. So what is this submatrix going to look like? So it will certainly include some rows of I, otherwise the result is immediate. So which rows, what will this intersection of, let me redraw this a little bit. Let me redraw this again, just to make it more clear. So here's A, here's I, here's my matrix, and just for, I'm going to take some rows of A, some rows of I, and some columns. And now I'm asking, what does this intersection look like? And unless this intersection basically looks like this, where I have ones here. And so imagine that I, in fact, take what I shaded in. Well, since I has ones here, let's say below that, then what I've taken is going to be is going to have a block of zeros, the portion of it that came from I, which means that the matrix, the square submatrix, would have a row that's entirely 0, and therefore the result holds because the determinant is going to be 0. It's going to be a ranked efficient matrix. So that's all good. So the only interesting case that remains is when the submatrix, the square submatrix that I take, has this form. It has to have ones here. Here it can have any values. This is not just one row on top. It's just things that come from A. And I don't care what those are. Up in this corner is a proper submatrix of A. And then here I have zeros. So in other words, if I were to somehow shuffle to redraw this picture one more time, here is A on top, and here's I. What I'm saying is that the only, the square submatrices that make sense, maybe I need to choose a different color. The square submatrices that make sense must look something essentially like that. So I'll have ones coming down here for I. Then, this is zeros because the ones in I continue. Sorry, I didn't draw it too well. And then I have some portion of A hat, and then some other stuff that I don't care about. So I need to show that that this thing has a determinant that's equal to +1, -1, or 0. And how are we going to do this? Basically, whenever we're dealing with determinants and these types of matrices, we're expanding by minors. How are we going to expand by minors? We're going to expand by minors according to one of the. We're certainly not going to use any of those rows. We're going to expand by minors according to one of the rows, say, of the identity portion of the matrix, and all of those, as you can see, are going to be basically so by expansion by minors, and because A hat is a square submatrix of A, the determinant is indeed going to be in 0, +1, or -1. And as an exercise, you should fill in exactly the details. So what I say expansion by minors, but along what precisely? And then how does this work? So fill in the details of this, because this kind of argument is generally very useful. Okay, so now let's actually prove something else that is interesting, and that is that the converse holds as well. So in other words, let's show the following. If A has independent rows, as we usually assume when we have an LP in standard form, then the polytope, which is equal to x such that ax equals b, I just wrote this before, and x non-negative, is integral. When I say a polytope is integral, again, it means its extreme points are integral. Is integral for every vector b that's integral, if and only if A is totally unimodular. So we already proved one direction. So one direction, that if A is totally unimodular, then this is integral. That follows directly from this lemma. That was essentially the second result that we stated. But what's interesting is that the converse also holds. So in other words, if for any b I put in here that's integral, this results in a polytope that has only integral vertices. The only way that can happen is if A is in fact totally unimodular. So A in this case is a matrix that is short and wide, and we know what any extreme point is going to look like. It's going to look like, I'll choose my basis A, B. So clearly, it's enough to show. It's enough to show that A, B is totally unimodular, because any square submatrix of A is a square submatrix of some basis AB for some B. So it's enough to show that this is totally unimodular. And here I'm going to rely on the first definition that I gave of total unimodularity, that AB is totally unimodular. And note again, A, of course, in all of this, whenever we say total unimodularity, it is part of it is an assumption that I have to have zeros, ones, and minus ones. So AB is totally unimodular if and only if its inverse, AB inverse, is integral. In other words, more specifically, has entries in 0, 1, and -1. And that is equivalent to writing that AB inverse times any vector v is integral for all integral v. Okay, so now what is it that I need to what is it that I need to do? I want to show that if I have an extreme point, then that's integral, then AB is totally unimodular, which is the same as writing that AB inverse is integral, which is the same as asserting that AB inverse times V is integral for all integral V. So let's do that. So again, just a recap from the previous slide, I need to show that A, B inverse times V is integral when V is an integral vector. And the way I'm going to do this is essentially by showing that AB inverse times V is an integral scaling away from an extreme point. Since an extreme point is integral by assumption, then if you sorry, I didn't mean scale, translation. If I translate an integral point by some integral vector, I'm again going to be somewhere integral, and that will basically show me that A B inverse times V is integral. So I need to make an integral extreme point. I need to find an integral extreme point that is a translation that's integral away from this vector AB inverse V that I'm trying to show is itself integral. Okay, so let's choose an integral vector y such that z is equal to y plus this AB inverse, AB inverse V, is greater than or equal to 0. Okay, so no assertion about AB inverse B yet. So certainly I can do this. I can choose a big enough integer vector y so that this is true. Now multiply both sides by AB. So AB times Z equals AB times Y plus V. And remember that V is integral. So what does this imply? Well, Y is integral. AB is a square submatrix whose only elements are 1 and minus 1 and 0. So AB times Y is integral. So that means that AB times Z is integral. Okay. So we're almost there. So our matrix A, remember, is something like this, and there are some columns that we chose, the ones in B, and then there are the things in its complement. So as we did when we were talking about simplex method, I'll just put those in front. So this is AB and AB complement. So now let's take the vector Z tilde, which is basically Z padded by zeros. And again, I'm using my usual abusive notation. I'm assuming that the columns B that I chose are the first ones. But of course, what I really mean here is I'm putting Z into the columns, into the entries of Z that correspond to B, and I'm padding with zeros everywhere else. So what's A Z tilde? Well, A Z tilde, just doing this multiplication, it's AB complement, Z 0. So this is equal to ABZ plus AB complement times 0, which is ABZ, which is equal to ABY plus V. Which is equal to ABY plus V. Okay, so what do we know? So first of all, we know that ABY plus V. We said that this is integral. So let's call this. Let's define this. I guess I went in the reverse direction. Let me write it more clearly. Let's let B equal ABZ. This value. And now let's consider the polytope. This is where we're going to use our assumption. P is equal to AX equals B such that X is non-negative. We know that B is integral. So any extreme point is integral. But we just designed an extreme point. So z tilde is an extreme point of P. Hence, z tilde is integral. But if z tilde is integral, z tilde is just z0, so that means that z is integral. And now, just unwrapping, what did we have before? Z was exactly what we initially said was our goal. We want to show AB inverse V is integral. What we showed is that AB inverse V is an integer translation away from an integer point. So this means that AB inverse V is integral, and therefore that means that that total unimodularity, that integrality implies total unimodularity. So again, what is the key link that we didn't show here? That is the equivalence of those first two definitions that are on the very first slide of this lecture. Okay, now let me follow up with a simple corollary. I'll write it as a theorem due to Hoffman and Kruskal, which says that if A is integral, and again, I'm writing integral, but when I say the matrix is integral, I mean it has -1s, 0s, and 1s. If you're ever hoping for total unimodularity, it has to be that. But when I say B is integral, I'm just implying that it has integer coefficients. So I guess I should be a little more clear. So if A is integral, then A is total unimodular if and only if for every B integral P, which is equal to x and ax less than b, and now x non-negative. So this is a little different than what we had before because it's not in standard form. This is integral. And again, the proof is very, very similar to all of this. Proof, it follows from above. And then, similarly to the lemma, I guess, follows from above, and the fact that A is totally unimodular if and only if A with the identity appended as columns is totally unimodular. And that's very similar to the lemma. So this is, again, just another result illustrating that when you have total unimodularity, whether you have standard form or you have inequalities plus non-negativity, all of these things are going to result in total unimodularity. We're going to stop here and pick it up in the next lecture to talk about how this relates to problems that arise from graphs, like the problems that we've been discussing.